Hello, welcome to my presentation. My name is Juan Francisco, and today I'm gonna present my work entitled Three-Dimensional Seismic Distribution and Morphometric Analysis of the Aptian Presal Barra Formation in Santos Basin, Brazil, which was developed at the Laboratory of Geological Reservoir Modeling, MGR, here at CEPETRO Unicamp. This work has been developed along with most of my colleagues and some external advisors. As a summary for today, I'm going to start with a short introduction about the topic, the objectives of the work, and the method that we use to obtain the results. Later, I'm going to show you the results from the seismic facies classification and the measurement analysis, and finally show you the discussion with the integration of well data and the conclusion and some useful references. As an introduction, we have that presal carbonates from the marginal Brazilian basins, in this case Santos Basin, has gained worldwide recognition due to their importance as the principal reservoirs of several giant fields. In this case, we are gonna study the study area close to the Santos Odor High, and in particular the Barra Formation. Barra Formation is the main reservoir, which was deposited within an alkaline lacustrine paleoenvironment on the late rifting and sack phases during the lower Cretaceous. The lithotype of this formation depends on the origin and composition of these sediments, separating into three main groups: the in situ carbonates, mostly shortstones and spherulistones, also the mudstones that are characterized by carbonate muds and magnesium-rich clays, and the reworked carbonates, mostly backstone, rookstone, greystone, uh, that has been described by different authors during this last year. The reservoir models of the lithotypes needs in-depth understanding of the conceptual model, paying more attention to the detailed three-dimensional distribution architecture and the areal distribution of the faces. For this reason, some of the objectives that we planned to explain in this work are based on the identifying the morphologies of the seismic reflectors and determination patterns of this presal reservoir from the Barra formation to extract a general stratigraphic framework and the record of erosional activities or the positional characteristics, architectures that may affect the facies distribution of the Barra formation, and analyze the morphometric measurements of these seismic facies to integrate with the information of wells, maybe obtaining insights into the reservoir quality, lithofacies distribution of the Barra formation inside the study area. The data that we use is a PSDM 3D survey covering approximately 600 square kilometers, and the interpretation of main horizons, in this case and nonconformities from the Barra formation that were calibrated with well tops and logs from 16 wells regionally distributed over the study area. The method is based on two steps: identification of the principal seismic patterns using seismic attribute, and the analysis of the measurements to describe the morphometric characteristics and correlate it with information from wells. Taking into account the 3D survey, we select uh, 7 patterns or main seismic phases, like the table on the right. When we describe the seismic feature on seismic image, the internal seismic characteristics that are based on the amplitude, geometry, continuity, and termination patterns, the external morphology, which describes the way that are distributed on the area, the variation of these seismic phases, the occurrence according to the structural maps, faults and structural heights, and a predominant mineralogy based on multimineralogic well logs. All of these phases are taken into account into a scale of 100 to 250 meters on vertical scale, or approximately 1 to 2 kilometers laterally. On the first step, we are going to take into account the first 3 seismic phases. The parallel seismic reflectors consist of horizontal to sub-horizontal seismic reflectors with high amplitude and really continuous reflectors that are organized on packages of 200 to 300 meters and are identified basing ward of the western slope of the carbonate platform. The mountain phases, on the other hand, is characterized by low to moderate amplitudes, convex up shape, release continuous to semi-continuous reflections with bidirectional down-ups in this case. And they occur mostly related to the structural height and present 2 variations, the folded case and the undeveloped case. The wedge seismic phases present inclinate truncation patterns which describe convex down shape against the structural heights or the throw of the major faults. One of the variations of these seismic phases is the complex arrangement of these phases, and the occurrence is mostly on the structural loads. Now we continue with the last 4 phases in this case. Now the low angle clinophore seismic phases correspond to a oblique parallel to slightly interrupted seismic reflectors, with high amplitude keeping basing work. There are some variation, in this case the interrupter low angle clinophore and the oblique parallel low angle clinophore. They are close, most of the occurrence is close to the structural highs. The right seismic phases is related to a thin convex up to thick parallel geometries over the truncation of the structural height at the top of the structural height. There are some variations too. For example, in this case, the uncovered and the parallel description of these seismic phases, and most of the occurrences in the structural height. On the other hand, the external mount seismic phases is a combination of high amplitude reflectors with convex up shape on the marginal part of the area that change to unlapping towards the truncation of the structural height. and sometimes it's diffused, the onlapse, and sometimes it's really clear the amplitude of these seismic patterns, termination patterns. Later, the high angle clinophores that are related to this marginal slope on the eastern part that have some variation. Some of them are characterized by top laps on the on the on the western part and down laps on the eastern part. Some of the variation, the divergent, that is not clear because the amplitude is really low, and most of the occurrence is close to the slope, close to the structural heights. Now I'm going to show you some characteristics that help us to identify the seismic facies. In this case, we use several attributes, and for example, RMS, similarity, relative acoustic impedance, the unsupervised neural network to classify the seismic waveform, seismic relief, in this case, that help us to highlight the morphologies. On the western of the attributes, the attribute displays local flatness zones, most of them related to parallel seismic reflectors and the intercalation of contrasting amplitudes. As there is evidence in the RMS and also in the seismic relief, you can see these characteristics. In the internal convex subshape related to the internal mounted seismic facies, you can see that it's really challenging to identify because they show erosive surfaces in this case that are mainly flat and generate gentle lateral slopes that are difficult to identify. However, external mounted shapes in this case are highlighted by the intercalation of contrasting amplitudes, for example, here in the relative amplitude impedance or in the unsupervised neural network that help us to identify the well-developed convex subshape to the western slope. Relative relief and similarity help us to highlight the lateral clinoforms, in this case, and this one and this one, by the divergent geometries and the characteristic that is really is adjacent to the mounted seismic facies. Besides, the morphology of the mounted facies depends on the structural position of the faults. For that reason, these structural attributes are really useful for us. It's easy to see that the seismic facies on maps, on map view, is easy to identify. For example, in similarity, it's easy to differentiate the external mount by the green arrows. And in RMS, is easy to identify the internal mounts because the low amplitude that these seismic features generate and highlights in these attributes. On the left hand, we can see the distribution of seismic facies, the external mounts that is separated in the onlapse and the convex subshape. The right, that is in this part in black color, the clinophore that is separated in the western side and in the eastern side, depending on the deepening of the clinophore. The internal mounts that are characterized by the blue color, in this case related to the faults, and the wedge and the parallel or distal seismic facies that are related to the yellow and the gray color. The method of measuring the seismic phases was based on the seismic grid that systematically take into account the angles, the distance, the weight, the height of each one of these morphologies that we indicated before. For now, the mounded shapes and the clinophores, in this case, and this case, and this case, were taken into account for the analysis. In this section, we show each one of these members that were measured using this method. On the left, you can observe the systematic grid and the map of the seismic phases. The external mound was divided into three members according to a morphometric analysis. And in this case, we focus on the distance of the on the distance from the basement and the angle of the onlap of the seismic reflectors. All the morphometrics are shown from the south to the north. Member 1 is characterized by decreasing on the distance of the angles of the distance and angles of the onlaps. Later, member 2 decreased the distance of the from the basement, but increase the angle of the onlaps. And to the north, the member 3, the third member, decreased the angle and the distance from the basement, almost showing a development of the feature over the basement, like in this case. So for a better characterization, we taking into account some called the width and height range, which allow us to analyze the shape of the mounded facies. The lower the ratio is, it should looks like a cone. Otherwise, the higher is, it should look like a convex up disc shape. In our case, member 1 started as a disc, later going to the north, becoming like a cone, increasing the angle in its flanks. Member 2 preserve the same shape along the area in this part, and member 3 start to becoming a disc before the distance of the basement start increasing. In this case, it start like a disc, and the distance of the basement increase later to the north. If we compare it with the distance from the basement, we observe that the variation on the shape have some kind of type of correlation with the shape of the feature. The shorter the distance, the steeper the flanks of the mounds will be. Now, for the clinophore, we taking into account the angle of the seismic reflectors, and also the length of the clinophore. We separate into three main groups, 1, 2, and 3, the orange polygons, over the black square. We observe that the distance of the clinophore is affected by the angle, which in turn depends on the slope of the basement. When the length of the clinophore decrease, for example, in this case, or in this case, the angle of those increase. You can see that the difference between the angle and the distance in all of three cases. For now, the internal mount, we use the same criteria than the external mount. The lower the ratio is, it should look like a cone. Otherwise, the higher is, it should look like a convex up disc shape. In this case, we compare two internal mounts, the close to the basement and the affected by the displacement of the fall or the throw of the fall. In the case of the mount close to the basement, its shape is affected by the distance that separates from the basement, and it looks more like a cone when the distance from the basement decreases. The opposite case to what happened in the external mount. For the member that is affected by the displacement of the fall, When there is a little or short throw, the shape is more like a disc, and when the displacement or the throw increase, it begins to become like a cone with narrow flanks, more like a pyramid. Now, comparing with the well data, we observe that two lithofaces trend are observed based on the relation of the seismic phases distribution. Um, the western trend that is characterized by higher percentage of in situ lithophases, ferrolimestone, soapstone, and the eastern trend that is characterized by the difference in the percentage of reworked phases in a mix with in situ phases. On the other hand, the reservoir quality has a ester trend with low reservoir quality affected by influenced by high silica content, and the ester trend that is distributed with high reservoir quality or the best quality of the reservoirs in these three wells with some differences in the percentage and low influence on the on silica content. Taking into account the distribution of the seismic phases on the wells, we can observe that these two wells in red are related when the folded of the trough is graded. The shape of the mound looks more like a cone, preserving increasing in the amount of the reworked phases, for example, in this case, from 60% to 30%. While the in situ phases is decreasing. If you can see, for example, the ferrolyzed on the some decrease in a some units uh, for these two wells. Now, close to the basement, in the yellow ones, the wells in yellow, these and these, the distance of the basement may influence the distribution and the shape of this mount. In this case, the percentage of the reworked phases, for example, rootstone, greystone, paxton, decrease since the shape of the mount looks more like a disc. For that reason, the in situ phases increase at some point. For the external mount, the well in green show us how the distribution of the lithophases is different from the other two wells in red. Here the lithophases are mixing in, and its percentage are similar H1. If you can see the stripstones, ferrolyzed stones, and the reworked phases. Maybe the distance from the basement influence the mix of the sediments, since the distance is larger than the in other part of the field to the north. And obviously the preservation or the good quality of the reservoir in this part. However, the wells in red show us how the reworked phases may dominate the increasing to the north of the best reservoir quality associated with the reworked phases. And when the shape of the mound increase, I mean the flanks of the mound increase like a cone, the reworked phases is increasing to the north. What show us how is the influence of the measure of the shape of the features, seismic features, on the distribution of lithophases and reservoir quality. As a conclusion, we differentiate 7 seismic phases. 4 of them were mapped, the mount, the clinoform, the ridge, the wedge, and the parallel seismic phases. And the most common are the mounted phases and the clinoform phases that are associated with the structural highs and the folds on the field. Seismic phases morphology and the measurements are influenced directly by the distance and the angle from the structural highs, and any geometric characteristic of these seismic reflectors are affecting the distribution and the influence of the morphometric analysis. Obviously, the important part is how the distribution of the lithofacies and reservoir quality are influenced by the geometry of these seismic facies. As we saw before, the difference in the western and the eastern trend are related to the geometric characteristic and morphometric measurements. And this highlights some changes in the amount of silica distribution and rework and in situ phases. Some useful references that we use for this work. Thank you all our collaborators and all our sponsors and funding. And if you have some doubts or questions, please type me an email. Thank you so much for your attention and time.